right? Write in ALP to generate a square wave of 50% duty cycle on P2.3. Use timer 0 in mode 1 to generate the delay. Use initial value of FF4E for the timer and a crystal frequency of 11.0592 megahertz. Calculate the frequency of the square wave generated. Calculate the frequency of the square wave generated. Everyone, did you try this one? Right? We should get the delay as 386.26 microseconds. Right? If you see this, right, the same problem what we have, we calculated the delay for this one. Right? Here the initial value is FF4E here, and you need to generate the square wave on the port P2.3 here, right? And a crystal frequency of 11.0592 megahertz. Calculate the frequency of the square wave generated there, right? Now how did you do this one now? How did you do this one, right? If you can see from this one what we had, right? The initial value was FF4E there. And the first you need to follow the steps. The first step what you need to follow in order to generate the time delays, you need to initialize the T-mode register. First I'm initializing here, and it is the timer 0 in mode 1. So that what I have, move T-mode comma hash 01H. So that the lower bits 0 and 1, the bit 0 is 1, the bit 1 is 0 there. So the timer 0 is selected to operate in mode 1 there. First I will initialize the T-mode register, right? I will send that value, right? Next move TL0 comma hash 4EH, because you can see the lower, we need to initialize with this initial count values, right? The lower byte is 4E there. So that what we have, the TL0, why it is TL0? Because timer 0, right? 4E, and again move TH0 comma 0 FF. I initialize this the timer 0 with FFH because the higher byte is FFH there, right? First I've done that, right? The T-mode register is set now. After that I've initialized the TL0 register and TH0. Next which is the next step what we have it here? Start the timer what we have it, right? Start the timer. Before that what I do, I say something like complement P2.3, so that maybe if it is before it was 0, when I use complement P2.3, I make sure that now it is 1 now, right? Now I call delay. Delay. In call delay, what we have it? Set B. That is the third step what we have. The set B TR0, right? Everyone can see that. What were the steps we had? Start the timer. First thing, these two steps you have done it. Next is the start the timer. How you do the start the timer? Set B TR0 there. Set B TR0, right? Now when I use this instruction, what will happen? It will start the timer 0. That's the reason TR0 there. Next what we have, JNB TF0 comma wait. Now what I do, since the timer has started, the timer 0 is receiving the clock pulses. As it keeps on increasing, receiving the clock pulses, what will happen? It will keep on increasing the number of counts in the timer there, right? And whenever the count reaches the maximum value, we know that since it is an operating in mode 1 16-bit timer, right? Whenever it reaches FFH, right, that is the maximum count what we can have in mode 1 there. Now what we can have, after when it increases that, it will reset to 00 and it will set the overflow flag to 1. Since the timer 0 is used in what? Mode 1 there, it will set the TF0 flag, which is the flag for timer 0. This flag will be set. When this flag will set, it will come out of this loop, the wait thing what we have it, right? It will come out of that one, right? Next what we have, clear TR0, right? If you see this instruction what we have, we are doing that. The fourth point what we have, keep monitoring the timer flag with the JNB TFX comma target, right? We keep on monitoring whether the overflow flag is set or not. Whenever it is set, what will happen, right? It will set the overflow flag there, right? And this flag will be set to high. Once that is set, what you do, you stop the timer there. How you stop the timer here? Which instructions do you use for this one? For CLR TR 0, stop the timer, right? Next, what you have, you clear the overflow flag also, CLR TF 0, right? Since it is a subroutine, you should have a return instruction at the end. You return a RET instruction there, right? Instruction which is written there, so that it will keep on increasing. So that what will happen now, for this much of delay, if you see the delay is what we have, the JNB TFO 0 comma wait, right? It will keep on monitoring till the counter, till it reaches the maximum value, and when it resets to 00, it will set the overflow flag to 1 here, right? The delay is because of this JNB TFO 0 here, right? And this delay is dependent on what, the what initial value what we give it in TL0 and TH0 here, right? If you start from 00, what will happen, right? The value is will be more. It has to keep on monitoring till it reaches what, how many number of 65535, right? We know the number of states, the number of the counts what we can have it in timer mode 1, right? 65536, right? That many number of counts. It will keep on counting till that, so that it will be still waiting for that here. It will be still waiting to overflow flag will be to set. When it will be set, after only when it is 65536 counts, only after that the overflow flag will be set, right? The delay is more when the initial values are 00. When the initial value is FF4E, if you can see it's on the values, now the count, right? The count values is less to reach the maximum value of FF there, right? So that the delay will be less. If the initial value is 00, the delay will be more for overflow flag to set there, right? So the initial value, the FF4E is given here, and the crystal frequency is given as 11.0592 megahertz. What it says, you calculate the frequency of the square wave which is generated here, right? Now here it is, timer frequency is nothing but what were divided by 12, so that you get it as 921.6 kilohertz. And so that what is the time period for this timer? We know that it is 1.085 microseconds. What we understand by this one, as I said, right? The timer increments the count by 1 for every 1.085 microseconds there, right? Now how do you calculate the time delay for this one? 2 into number of counts to roll over into 1.085 microseconds. Now how do you calculate the number of counts to roll over? The number of clock pulses which are required to roll over here, we know that is FF. And what is the initial value which is loaded into timer 0? FF4E there. So that what we have, plus 1. And if you convert, subtract this one and convert to decimal, in decimal equivalent of that will be 177 states or count are the clock pulses, plus 1. Why it is 1? Because one extra clock pulse is needed for rollover, so that it will be 178. So that what is the time delay for this one? 2 into 178 into 1.085 microsecond. So this is equal to 386.26 microseconds there. Therefore, the frequency of the square wave generated is nothing but the inverse of this one, 1 divided by time delay, which is 1 divided by 386.26 microseconds. So that what is the frequency of the square wave which is generated with the initial value of FF4E, 2.5889 kilohertz. Everyone please mute your mic. 2.5889 kilohertz there, right? Right? Everyone understood this program here? Right? So that we got the time delay and the frequency is 2.5889 kilohertz. The next problem what we had, what was the next problem we had? Find the frequency of the square wave generated for the program given, which generates a square wave on pin P1.5 using timer 1. Assume crystal frequency of 11.0592 megahertz. Right? Now here the program is given to us, right? Now you need to find the frequency of the square wave generated for the program given, right? Which generates a square wave on pin P1.5 using timer 1, and the mode here I have not mentioned the mode. You can see just by looking at the program, you know the mode is what we have. It is 10, so it's a 0001. So that bit 4 is 1, bit 5 is 0, right? Those bit 4 and 5 is for timer 1 there, so that the timer 1 is operating in mode 1 there. It is selected to operate in mode 1 there, right? And also you can see what is the initial value what we have here. The lower byte is 34H, the higher byte is 76H, right? So the initial value what we have it to start the counter is 76, 34H there. Next what we have, you need to start the timer. Set TR1. Why it is TR1? Because the timer 1 is used here. Which is the bit to start the timer 1? It is TR1. Set has changed it to set B. Set B because it's a bit. Set TR1. Right? You're setting that bit. Next what we have? JNB TF1 comma big comma back. What is TF1 here? Since it is timer 1, which overflow flag will be set? It will be TF1 overflow flag will be set. It will be keep on monitoring till the TH and TL becomes what? FFH. Whenever it reaches that and resets to 00, it will roll over, right? And it will set the flag, the overflow flag to 1. Once the overflow flag will be set, it will come out of this instruction and it will go to the next instruction, CLR TR1. What is this instruction does? It will stop the timer 1. That's the reason it is TR1 here. Next what is CPL complement P1.5. Maybe because before it was maybe 0, now you're complementing 1 so that it is 1 now, right? If that bit is set to 1, clear TF1, SGMP again, SGMP again there. So that again this will keep on changing, right? So that if you see this one is for, if you see this instruction what we have, GNB TF1 comma back, this is for 1 half cycle. This is for 1 half cycle, right? So that how do you do this one? This is similar to the same program. Now only the initial values have changed. Initial value is 76, 34H. The frequency is still the frequency is still the same, 11.0592 megahertz. So that how do you do this one now? The same program will return it. What is the initial value we have? 76, 34H, and the crystal frequency is 11.0592 megahertz. We know how to calculate the timer frequency and the time period. The time period for this one is 1.085 microseconds. So that what is the time delay? What is the formula for this one? 2 into number of counts to roll over into 1.085 microseconds, right? And how do you calculate the number of counts to roll over, or the number of clock pulses needed to roll over here? Final value minus initial value plus 1. Since it is hexadecimal, FF minus 7634H plus 1. If you subtract this one, what will happen? You get one hexadecimal number, and that hexadecimal number convert into decimal. When I convert to decimal, what you get? 37, 35, 27, 5. That is the decimal equivalent of the hexadecimal equivalent after subtracting the final value and the initial value plus 1. So that what you get here? 35276. 35276. So that what is the time delay we have it? 2 into 35276 into 1.085 microsecond. How much you get it at? 76,548.92 microsecond. That is the time delay what we have it. So that what is the frequency of the square wave generated? It is nothing but 1 divided by the time delay. So that you get it as the frequency of the square wave as 13.064 hertz. 13.064 hertz here. That's everyone understood. Now we know the program is given to us, right? Now we know how to calculate the time delay or the frequency of the square wave which is generated for the given initial values. The program is given to us. In that program, the initial values is given to us. Using that initial value, we know what is the frequency of the square wave which is generated or the time delay of the square wave signal which is generated. We know that. As you can use, you can, if you want, you can go to the Keel software and try to run this one and how the program is working. You can see it on the peripherals also there, right? What we'll do is we will go to the Keel software, right? I'll say how you would run this one, right? We'll go to the Keel software. Now we'll write, I have this open here. Maybe I have one file, maybe I can write it as some other file, right? I have written it as some 6 byte.asm. Now the first thing is we need to follow that steps. What are the steps we have, right? The first one what we have is move. We need to initialize the tmod register, comma, right? Hash. Maybe if I'm using timer 0 h, timer 0 which I'm using, I'm initializing those so that the timer is operating in which mode now? Maybe now the timer 0 is selected in mode 1 there, right? Next what we have now, next we need to initialize the registers there. Which registers? Since it is timer 0, TL0 and TH0. TL0 comma hash. Maybe we'll start with some other values, maybe F A H, right? Since it is alphabet here, start with 0, right? So that what we have done, so that the TL0 is equal to what now? FAH there. Similarly move now TH0 comma is equal to hash 0 FFH there, right? So that what we have it here, so that the TH0 is equal to what after executing this one? It will be FFH, right? We initialized tmod register, we initialized the TL0 register and TH0 register. Next what you need to do, now you need to start the timer. For that, to start the timer, use the instruction set B, right? TR0. Why it is TR0? Because the timer 0 here, timer 0 what we have, right? Next what we have, you can write the comment as maybe start the timer 0, right? Next what we have it for this one, next one J, which instruction we have? J NB, right? TF, now TF0 or TF1, it is TF0 because the timer 0 is selected, comma, I'll say something like again here. Where again here? Again the same instruction, it has to keep on monitoring this bit till the timer resets to 00, right? Till that overflow flag is set to 1L. It has to keep monitoring that, right? Next what you do, once you do that, and whenever the overflow flag set is set, now you stop the timer. For that one, CLR TR0, right? Next what we have? CLR TF0, right? We are setting that. We are not writing a subroutine, it's just a simple program what we have it, so that this could be written something like this, a more structured program. Right now we have the comment For each of the program, you should always write the comment so that you know the flow of the program, how the program is flowing, and what instructions are trying to do it. Right? This is the program what we have it. Right? Let's keep on running this one. Now we don't have any errors here. Right? It says that we should start with an end. Right? It always should start with org start and end. That's now go to the debug mode. How the timer will start. I can see this one. Now go to the peripherals. In peripherals, you have timers there. Which is a timer we have selected? Timer 0 there. So that the timer 0, what we have it. Now you have different modes in this one, peripherals, right? Everyone can see this window. You can see the timer window there. Now we have different modes. Mode 0, mode 1, mode 2 and mode 3. Now it is in which mode now? It is mode 1 there, right? So that what you can write for this one now? 01H, right? Now if you can see this one, the TCON registers is there, TMOD register is there, TH0 register is there, TL register is there. We have the overflow flag for this one. We have the set flag. Then you can see that it is stop now, right? Now if you see the initial status of the timer 0, it is not running, right? It is in stop state now, right? Now we can run this program, this one. Now if you can see now what we have it, you can see the tmod is 01. You can see the tmod register value has changed to 01 there. Next instruction what we have, we'll go one by one instruction, right, and try to see how the programs are working and how it is incrementing the number of counts there, right? So that what we have it now, this one. Now that will execute move TL0 comma hash 0FAH. So that what we have, you can see that now since we executed that instruction, the content has changed to FA there, FA, right? Next set B TR. Next we have move TH0 comma 0FFH. Yes, everyone can see the peripheral, the timer 0 peripheral window there, right? Now run this one. Now the TH0 is FF there, FF, right? Next what we have, next set B TR0, right? What is this instruction does? It will start the timer 0. As you can see here, now the status is what? Stop now. When I execute this one, what will happen there? The status has changed to run there, and you can see that this TR0 bit has set to 1 there, right? Now the timer has started, so that now the timer 0 is receiving the clock pulses. As it keeps on receiving the clock pulses, it will increment the number of counts by 1 in the timer 0 register, right? Now what you can see, that is, you can see this one, what we have is FB there. Now what we have, this instructions could be written as what now? Now execute this one. Now you can see this, the overflow flag is 0. Now it will monitor, right? Now it is FD. If you see here, it has like FB was there, FC and FD, because this instruction takes 2 machine cycles. The JNB TF0 comma, again what we have, this instruction will do 2 machine cycles, so the count has incremented by 2 there, right? It has FB, now it has FD there, right? It is incremented by 2 because of this instruction, right? Again it will increase the count. Again it was FD, now it is FF, right? Now what again you will execute this one, what will happen, right? Since that instruction will take what, 2 machine cycles, it has rolled over, reset, and it has turned to 0 1 there, right? Now what happened, now this bit is set, now TF0 bit is set. So since that bit is set, it will come out of execution of that instruction, so that now it is pointing to clear TR0 now. It is pointing to clear TR0. Now this instruction will stop the timer. Stop the timer so that the TR0 bit is set to 0. And also I'll make sure that this bit is, the TF0 bit is also is reset, so that what we have, this TF0 bit is set to 0, right? This is how you see how it is instruction is running, right? Maybe now, and also you can see the first program what we have, the first program what we had, we'll run that program too, right? The first program, and see how it is working there. We know how this program works. We'll try to copy this one. And we need to copy the subroutine program also. You can put it anywhere here. And we'll try to save this program and see if there are any errors, right? Since we know this program, we know how this program is working, right? We'll see how it works, right? I'll go to the debug window there, debug window, start this one, right? The timer what we have it here, right? It says now which timer are we using? We are using timer 0 only. We are using the timer 0 instruction only there, right? So that what we have, we have selected the timer 0 here, and it is operating in which mode now? Timer mode this, right? Timer mode 1. Now try to run this code, how this code works, which is the instruction what we have. Run this one, what we have, move TL0 comma F2, so that the TL0 register will be initialized with F2. Next what we have it, TH instruction what we have, so that the TH0 instruction will be initialized with FFH there. Next instruction we have complement P1.5 there. Now if you want to see the port also, the port, you need to set up the port there. Maybe already have this port there, right? P1.5, that is the bit which is used there, right? Now you can see the display type is bit here, so that we are displaying port 1 bit 5 there, right? Now run this one, right? A call delay, right? A call delay, you can see that in the logic analyzer here, you can see the value which is set here, right? I'll keep on running this one. It will keep on monitoring this one. Now it is F2 here, it is F2 there, right? Now I'm running this instruction. I will start the timer here. The timer has started. Now it keep on monitoring the overflow flag, right? Now it is F5, right? You can see from this instruction what we have, right? It has, if we CPL P1.5, right? Here it is, we call that as an instruction overhead, and because this instruction will take one machine cycle, so that it has incremented that F2 plus 1 will be F3, and this instruction JNBF TF0 will take 2 machine cycles, so that it has incremented by 2, right? Before it was F3, now it is F5 here. Again I'll increment this one, I will execute that instruction. Now it has incremented by 2. Again it will monitor if the overflow flag is not set, right? It will keep on incrementing the counter till the overflow flag is set. Now it is FB, FD, and it is FF now, right? Now it will be reset to what? Since it will takes 2 instructions here, now it is 0 1, and the overflow flag is set to 1 here, right? It is, set to 1 here, what will happen there now? Now it will come out of that instruction, right? Next, what we have, clear TR 0, right? TR 0, what will happen? Now it will stop the timer and the status has changed to stop, and this bit has become 0 here, right? Again, clear TF0, I'll reset that to 0, right? This bit has become 0 now, and I'll return from the subroutine, right? Once a subroutine, which is the program counter, will have the address of this next instruction, sjmp here, right? Now it will go here, again it will initialize that value, right? TF0 and this one, again complement p1 dot 5. The whatever value we had it before, now it will be complemented now, right? You can see it here. Now what you can do is, the best way to do is to run this instruction, right? I'll keep on this one, or else we can this continuous run. Since it is continuous, what we have, you can see the square wave which is generated here. You can see, everyone can see that one. We have the square wave which is generated there now, right? Since it is continuous, it is continuously running, and we are generating a square wave of 50% duty cycle there, right? And you can see here it is p1 dot 5, the port 1, the bit 5, what we have it there, right? Since it is continuous, it is continuously generating the square waves, and you can see in the timers that the tcon register is also changing, the tmod register is also changing, because we're setting the tr bits, and also we are clearing the tr bits and the tf bits, so that the tcon register is also changing. And since the timer is incrementing here, the th0 and tl0 is also changing the values, and also the status of the counter is also changing from stop to run to start there, right? You can see those things here. Everyone understood how to run on the Keel software, the same program, right? And open this peripheral window there, and in this peripheral window, if you are using timer 0, select the timer 0, or if it is timer 1, select the timer 1, and see how the program is working there, right? How the timer is working, right? We'll stop this one now. We'll stop this. And hope everyone understood how to run on the Keel software, right? How this subroutine is working, how the timers are working. We'll continue with this one. We'll see other problems. We'll go to the one more program what we have. Write an ALP to generate a square wave of 50 Hz with 50% duty cycle on pin 2.3 using timer 1 mode 1. Assume the crystal frequency as 11.05 megahertz. Everyone please mute your mic. Now with this one, everyone calculate this one, right? Now first, since here, write an ALP to find a square wave. See here, if you see this one, right? In the first three, what we had, everyone please mute your mic. Yes, you're unable to see this one. Just okay, yeah. Now if you see the first three problems what we had, right, the initial value was already given to us, right? It was what ff f2 in the first problem, And in the second problem what we had, right, again we had the initial value which was given there, ff4e, right. Since the initial value was given to us, we know how to write the program because we followed the steps to generate the time delay there, right. And you writing that program, we calculated how much is the time delay or what is the frequency of the square wave what we generated there. But there are scenario where what we have is, right, where we have a scenario where, right, we don't know, right, where we don't know the initial values, where we don't know the initial values. When I say we don't know the initial values, we don't know the values of the TL0 and TH0 registers there, right. Right, we don't know those values. Now how to calculate those initial values now, right. Here what we have is how to find the initial value for THX0 and TLX register when desired delay or the frequency is given for a square wave with 50% duty cycle and the crystal frequency is given as this, right. Now it is a reverse of that. Now the time delay is given for a square wave signal, or the frequency of the square wave which is generated, that frequency is given to us. Now you need to find the initial values which I need to load into the th register and TL register there. In order to find that one, these are the process what you need to follow. The first thing is divide the half period of the on or off portion of the square wave by 1.085 microsecond and get the number of timer clock pulses. The first thing is half period what we have it. The time delay is given to us. So when I say the time delay, it is a one complete period, right? It is nothing but the combination of on period plus off period. Since it is 50% duty cycle, we know that the on period is equal to off period. So that now only we need to take only the half period. Maybe it is on period or a off period. Once we know what is the on period or the off period, that period has to be divided with the 1.085 microseconds, right? Once you do that, what we get is get the number of timer clock pulses, what the number of counts we will get there. That will be one decimal number what you get it, and that decimal number has to be subtracted with 65536 because the number of clock pulses what we can count in mode 1 is what 65536 and minus n, that is minus n is nothing but the number of timer clock pulse what we got after this division, right. After this division whatever we got, that number you need to subtract it and you get one hexadecimal number, right. Maybe you get one decimal number and that decimal number convert to an hexadecimal number which will be YYXXX, and this YY is nothing but our THX register value and XX is nothing but our TLX register value. So that we initialize this TH register and TL register there. Everyone understood this scenario? In this scenario, what as I said here, the time delay is given, our frequency of the square wave which is generated is given to us. Now you need to find the initial values which I need to initialize the registers timer 0 or timer 1 there. And this is the process what you need to follow there. Right, we'll see one example here. Write an ALP to generate a square wave of 50 Hz with 50% duty cycle on pin 2.3 using timer 1 mode 1, assuming the crystal frequency is 11.0592 megahertz there, right. Now how you do this one, as I said here, you need to get the half period of the on or off portion here. Now here the frequency is given. What is the frequency of the square wave which is generated, which is equal to 50 Hz, right. Since the frequency is given, how do you calculate the time delay or the period for that square wave? It is nothing but 1 divided by 50 Hz, which is equal to 20 milliseconds there. So since it is 20 milliseconds, this is the complete, the total period, on period plus off period. What we need is only the half period. How do you get the half period here? It is 20 milliseconds divided by 2, which is equal to 10 milliseconds, right? Now what you need to do here, now you need to get the number of timer clock pulses. How do you get the number of timer clock pulses? You divide the half period divided by the 1.085 microseconds, so that the number of timer clock pulses n is nothing but is equal to 10 milliseconds divided by 1.085 microseconds. This you get it as one decimal number, 9216. Now we'll subtract this one, because we know that in decimal the maximum number of clocks cycles we can count is 65536 minus 9216, right? Here we got is a 9216. Subtract that one, you get in decimal as 56320. Convert this decimal number to hexadecimal. If I convert this one, what you get? DC00H, right? Since we know this values now you initialize the registers. Since in this example it is timer 1, I will initialize the TL1 with 00H and TH1 with DCH there, right? Once we know what value we need to initialize here, now write the ALP program, because it is given as you should write the ALP program. Now write the ALP program, and how you write it? Follow the steps which I given to you. Mode tmod, 0 1 0. Why it is 0 0 0 1 here? Because it is timer 1, right? So that the bit 4 is 1, the bit 5 is 0. That's the reason the tmod register is initialized as 10H. Next, TL1 is what? We already got the initial values, which is TL1 is 0 0, so that we have 00H. TH1 will be 0 DCH. Once we initialize this one, next you need to start the timer. Set B TR1. I've started the timer. Once I start the timer, now you need to keep monitoring the overflow flag, right? When it is set, you keep on monitoring the overflow flag, and whenever that flag is set to 1, what you do? You come out of that loop, right? And it will go to the next instruction. Which is the next instruction? CLR TR1. It will stop the timer 1, complement P2.5. Maybe before it was 0, now it will be 1. This bit will be set to 1. Again clear the TF bit 1 there, right? Now the overflow flag is set to 0. Again SJMP, again it will go here, right? TL1, again you initialize that value. Again you can keep on. If you can see this one, the JNB TF1, this is for one half cycle. Maybe the on period or the off period there. It is only for the half cycle what we have. In the previous example we use a subroutine. Here we are not using the subroutine there, right? And this is how you do it, right? Now everyone do for this one also. You can just note down this one. Write an ALP in 8051 which generates a square wave of frequency 10 kHz on pin P1.2 using timer 1 mode 1. Assume the crystal frequency is 11.0592 MHz. What is the minimum frequency that can be generated, right? The first you need to find for this frequency, 10 kHz frequency which is generated for the square wave, you need to find what is the initial values for the timer 1 register, right? Once you do that, next you need to find what should be the count of the timer register, so that the frequency, you can find the minimum frequency, right? We'll wind up in 5 minutes, right? We'll wind up in 5 minutes so that you can ready for the next class, right? The period of square wave is 1 divided 10 kHz, 0.1 milliseconds. This is, you get it as 100 microseconds. So that what we have it, the time delay is 100 milliseconds. The on period is 50 microseconds and the off is also 50 microseconds. Now you find the half period. What is the half period for this one? You get it as 50 microseconds. Now you calculate the number of timer clock pulses. So that when I do this one, what you get? 46.08. You should have a one decimal, right, as a whole value. Now we approximate to 46 here, right? Since it is 46.08, we approximate to 46 here. So that now we subtract 46 from 65536, so that in hexadecimal you get the equivalent as FFD2. So that you initialize this value with TH1 with FFH and TL1 with D2H. If we initialize with FFD2, what we get? We get a square wave frequency of frequency how much? 10 kilohertz there. So that you get it as what? Now you write the program, right? Follow the steps what I said, follow them. Next, one more thing what is given in this question is, what is the minimum frequency that can be generated here? What is the minimum frequency you can generate, right? We know minimum frequency will be generated when the minimum count at the maximum delay is loaded in the timer register, right? Now what we have, since you're starting with FFD2H, right, till it becomes FFH, when this TL becomes FFH, that is the amount of delay what we have it, right? What is the maximum delay we can get? If we can set this TL register and TH register with 00, right? Because you need more time for this register to become FFH there, right? That is the maximum delay what we have. So that what is the minimum count we can have it in this register TL1 and TH1, it will be 0, 0, right? What we have it. So that if the time delay, we know that F is nothing but F is equal to 1 by T. If the time delay is more, the frequency will be less. When the time delay is maximum, the frequency will be minimum there. So that the count is initialized with 0, 0, 0, 0 there. So that what we have when I initialize with 0, 0, what we get? The delay generated is how much? This many clock cycles what we have it. So that the time delay for one cycle will be 2 into this one. This is only for the half cycle, right? This is only for the half cycle what I said, because I said for this one, because this JNB TF1 is only for a half cycle, right? For the whole cycle will be, you get it as 142213.12 microseconds. So that what is the minimum frequency we have it? 7.0317 hertz. That is the minimum frequency what we can generate when the maximum delay is what we got is through minimum count of 0000, right? This is what we initialize with the timer 1 register there. Everyone understood this one, right? We'll continue with this one in the next class.